Okay, I wanted to go over a couple problems. I'm just kind of choosing the ones that I think are important for you to make sure that we understand. The first one is this one. This is a great problem. It says, does the pH of the solution in the reaction above increase, decrease, or remain the same as the reaction proceeds? Justify your answer. All right, so basically what we have happening is when they talk about a reaction proceeding, then that means it's going in that direction. Now remember, we talked about this. Whenever you are asked to discuss pH, your focus is always here, the hydrogen ion. That's your focus, and its concentration. As the hydrogen ion concentration goes up, pH goes down. As the hydrogen ion concentration goes down, pH goes up. So as we go in this direction, what's happening? The concentration of H plus is going down because it's being used up. It's being used up to get the product. So if the hydrogen ion concentration is going down, therefore pH is going up, or it's increasing. Okay, that's a really, really good problem. The next one that I want to look at is right here, right below this one. This was kind of confusing to students because we just came off this idea, right, that if I have a hydroxide concentration, that I can determine the hydrogen ion concentration using Kw, where Kw, is H plus times the concentration of OH minus. And the Kw for this is 1 times 10 to the minus 14. Remember, this is staying constant. I'm changing this. If this goes up, this has to go down. If this goes down, this has to go up because this is constant. This is a different problem. Basically, what I'm doing here, I'm changing the temperature, which means that Kw is changing. All right? So when I get here, it says that I have a pH of 6.63. Now, the pH drops, K is changing. How does that affect OH? All right, so let's go here first. We're going to do 10 to the minus 6.63. That is equal to the hydrogen ion concentration, and that is equal to 2.34 times 10 to the minus 7 molar. Now, in this case, if this changes, if H changes, and K is changing, basically what's happening is I'm shifting my equilibrium. So I have this equilibrium, remember. We've got Kw is equal to H plus OH minus. And we've got H2O in equilibrium with H plus OH minus. So what's happened here is that in order for this to change, I have to shift this equilibrium. But if I shift the equilibrium, then they both must change in the same because it's a 1-to-1 correspondence. So I'm shifting my equilibrium in this direction because this is going up, and I'm going to change this. So I get they have to be the same. 2.34 times 10 to the minus 7. So what I'm going to do now is I'm going to plug this in times, I shouldn't put a bracket around that other one, times 10 to the minus 7 is equal to what? That is equal to 5.5 times 10 to the minus 14. So my Kw has gone up from 1 times 10 to the minus 14 to 5.5 times 10 to the minus 14. Now, is the solution still neutral? Yes, because H plus is equal to OH minus. Does the value of Kw increase or decrease with an increase in temperature? Kw, if you look at, it's going from or pKW. Let's look at, oh, I see on here. Hang on a second. KW. There we go. The value of KW increases with temp, because we went from 1 times 10 to the minus 14 to 5.5 times 10 to the minus 14. What's going to happen to pKW? Remember, all we have to do to get pKW is take the negative log of KW, and if KW increases, pKW decreases, just like pH. Now, I want you to look at this. This is a chart of, let's see if I can move this over a little bit and help to see it better. This is a chart of the temperature dependence of KW. So as temperature is going up, KW is going up. Okay, so here's what I want us to do. This is just an added little exercise on here, but I think it's important to be able to do this. Okay, so this is my equilibrium, H plus OH minus, and KW is equal to H plus times OH minus. Now, it was saying that as I increase the temperature, KW goes up. In order for KW to go up, this times this must go up. These concentrations are going up. So what that means is that I am shifting my equilibrium in that direction. So if adding heat shifts my equilibrium in this direction, do I have an endothermic or exothermic reaction? This is Le Chatelier's principle. So remember that I always put the heat at the tail end of the shift, right? So if I put heat here and I add heat, that causes me to shift in that direction. Therefore, heat is on this side of the reaction, and this is an endothermic process. All right, so what we're going to do with this one, this is a great problem, because it really does help you understand the definition of what acidity is or basicity is based on the concentration of these ions. Okay, I'm going to take nitric and hydrochloric acid, both strongs, and I'm going to add them to a beaker. And it says, what is the pH, I believe, of this solution? All right. So pH, again, is the concentration of hydrogen ion. Now, when I add these, I'm going to put these up here. I'm going to single arrow it, H plus, I don't know why I put the bracket there, sorry about that, and Cl minus, and HCl goes to H plus Cl minus. Okay, what that means is that my hydrogen ions, if I want to find the hydrogen ion concentration, I've got to find out how much of these added together contribute to the hydrogen ion concentration in my solution. I can add them, and I've got a final volume, so that's moles of this. So remember, molarity is moles divided by liters. So I've got to find the number of moles of each. So that's what I'm going to do first. So the way I do this, I've got 100 milliliters of HNO3, 0.10 mole of HNO3, and that equals to 0.010 moles HNO3. Then I have 100 milliliters of, put that over 1,000, of 0.25 mole HCl. So that gives me 0.025 moles. So the total moles in solution is just going to be these added together. Once I pull it out of molarity and I just do moles, I can count them like I would marbles in a jar. I had this many marbles of H plus from this, and this many marbles of H plus for that. How many marbles of that divided by the total volume. It's the same thing. So think of moles as sort of counting. So that equals 0.010 plus 0.025. That is going to be 0.035. So I then divide that by my total volume. This is in milliliters. Remember, I'm going to have to do liters. And I take the negative log of that, and I get 1.5 as my pH.